Welcome. Today we're going to talk about attractive forces. In other words, what holds things together. So let's jump right in. And the biggest thing I want to make clear here is when we talk about intermolecular forces or attractive forces, these are forces between molecules. So if I have one molecule right here and another molecule right here, we're not talking about the forces inside the molecule. We're talking about the force that goes in between these two molecules that hold them together. Why is that important? Well, it kind of determines what state of matter you're in. So if you're a gas, the attractive forces are not very strong. Do you see how far apart these guys are? So they're not holding on to each other very tightly. If you're in a liquid, the particles are held really a lot more tightly, and in solids, they're held very tightly. So inter means between. So intermolecular forces are forces between molecules. Now, I want to make a distinction here because this is kind of important. Whenever we have molecules, individual molecules that are covalently bonded, the forces of attraction between those two things, let's say I have one molecule and another molecule, we call those intermolecular because they're between two molecules. When we're dealing with ionic compounds or metallic bonding, you have one ion and another ion, and they join together with these lattice structures. And when we talk about the pulling them apart, which is what boiling and melting are, we're actually talking about breaking apart attractive forces because we're not dealing with actual molecules. So to be clear here, when we talk about intermolecular forces, we are talking about only covalent bonds. So this is with covalent bonding. Now, I'm going to talk about three specific intermolecular forces. That we're going to start with the weakest, and these are called London dispersion forces. And they're kind of weird in this sense. Molecules or atoms, they have electrons. So what we know is that in every atom and in every molecule, electrons are always moving. They never stop moving. And at any point in time, if you were to go freeze, isn't it possible that you could have on one side of the molecule have more electrons than another, or even in an atom have more electrons on one side than another? And because of that, each molecule has the ability to then have a partial negative and a partial positive on one side or another, just based on how many electrons. So if I had one electron on each side of a molecule, they kind of even each other out and cancel out. But if I have like 10 electrons on one side and one electron on the side that has 10 electrons will be partially negative and the other side will be partially positive. And if it comes in contact with another molecule that's doing the same thing, they'd attract each other. So let's take a look here how this might play out. Now, in this diagram down below, we have an example of an atom and we have an example of a molecule. Now, if you take a look at this atom, you see how these dots here represent kind of a graph as if we dipped the electron in ink and it's kind of flying around here. And if you notice here, the electrons are evenly dispersed on both sides of the atom. Now, just due to their motion, if you go from here, from like 1 to 2, do you see how the electrons now have shifted and it's darker on this side? And when that happens, you end up with a partial negative on this side and a partial positive on this side. Now, as that happens, it can now attract things that have a partial positive and partial negative. And one of the things that we notice that occurs quite often is this. If this atom that has a partial positive, and so this side here is partially negative and this side is partially positive, comes in contact with an atom that it just has electrons regular, it can actually, this positive can actually attract electrons towards it, and you can end up with a partial negative on this side and a partial positive here. So if you have that happening, these two atoms between here and here, they will attract each other. That's called a London dispersion force. Here's another example of a molecule here that is nonpolar. See how we have a hydrogen and a hydrogen? They're clearly nonpolar. But as electrons shift around, you could have a portion, see how they drew it kind of darker here in blue, where the electrons have shifted this direction, and this side becomes partially negative, and this side becomes partially positive. And what can happen is it can induce or cause the molecule next to it that it's also nonpolar to match up with it. So see how this side right here is partially positive? It can cause this side, by pulling electrons towards it, to become partially negative. And that's what we see down here. See how the partial positive end right here and the partial negative end right here, they can attract each other. And this attractive force we call the London dispersion force. Now, what you should be aware of is that the greater your electron cloud, I'm reading from right here, the stronger your intermolecular force. What this means is more electrons, greater attractive force. And probably a better way of saying that is stronger LDF. What does that mean? Well, let's say I have a nucleus that has a bunch of protons in here, and on one side I have two negatives, and I have nothing on this side. And then in another molecule, so this is molecule 1, and in molecule 2, I have a nucleus, and I have like so many negatives on this side, and maybe like one, like, I will not be with you over on this side. Would you agree with me that overall this side will be much more negative than this side will? They're both partials. That's what this little note means. So, but of the two, comparatively, this London dispersion force would be stronger than this London dispersion force. Now, with dipole-dipole attractions, this involves two polar molecules. Now, we learned in the last unit how to draw dipole arrows and determine whether a molecule is polar. So if we have one molecule, and this is drawn right here, and one side is partially positive and the other side is partially negative, and it comes in contact with another molecule that has the same thing, they align themselves so that their positive and negatives attract each other. Now, since this is a polar molecule and this is a polar molecule, we say that these are dipoles. Two poles, oddly enough. So whenever we have a dipole and a dipole next to each other, we call those dipole-dipole attractions, or the fun way of saying that is dip-dips. So we say those are dip-dips. So every time we have polar molecules and you have trillions and trillions of them, they all line up with each other and they all attract each other, because no matter what, let's say this is a molecule, right? And this side is positive and this side is negative. And by positive and negative, I mean partially positive, because you only have full positive and negatives when you're dealing with ionic compounds. If that's the case, then they'll line themselves up to match up with every other molecule in the same way. So all of these right here, all these dotted lines are just showing how they attract each other. Now, what we need to know is that if we want to have something boil or change state, we have to actually break these intermolecular attractions, which is why the stronger the attraction, the more energy we have to put in. Now, hydrogen bonding, and remember I said there's three types. Hydrogen bonding is actually just dipole-dipole attractions, where a molecule itself, so again, if this is my molecule, one side of it becomes partially negative and the other side of it becomes partially positive, and then it attracts another molecule who has a partial negative and a partial positive. So again, we're looking between attractions between one dipole and another. But hydrogen bonding is unique in that if you have hydrogen attached to F or N, so it's fun. Simply because it's attached to F or N, the attractive force is going to be much stronger. And the best way to look at that is with water. So if you take a look at a water molecule right here, if you take a look at the bond between hydrogen and oxygen, since oxygen is a more electronegative atom, the electrons shift towards the oxygen. Similarly here, they shift towards oxygen. Now again, we talked about that last unit. What that means is that over here we have a partial negative and over here we have partial positives. So if you notice here, that's going to attract other water molecules, and you notice how the partial negative on the oxygen attracts the partial positive on hydrogen. This is exactly like what we had here, exactly the same thing, but if the attraction is between F or N and a hydrogen, that's a much stronger version of dipole-dipole attraction, so we call those hydrogen bonding. Even though it's not really bonding, and that kind of confuses students sometimes, hydrogen bonding is really an intermolecular force. Now, I'm going to show you this little table here, and this is kind of a big deal. So intermolecular forces, and we're kind of going down the chart here, and as you go down the chart here, you're ending up with stronger attractive forces. We'll call them AFs, right? But London dispersion forces are the weakest, dipole-dipole are stronger, and hydrogen bonding are the strongest. This is only with intermolecular forces, and remember, intermolecular forces only occur between covalent bonds. When you get to deal with ionic compounds or metallic compounds, where you have a full positive and a full negative, and that would be an example like NaCl, for example. Na is a positive, Cl is a full minus. That attractive force, which we talked about earlier on in the units, that attractive force is much stronger than any other attractive force between a molecule A and molecule B. This attractive force right here, the intermolecular force here, is always going to be weaker than the attractive force between full ions. So if we were ever to compare something like water, which is a covalent compound that has hydrogen bonding, to something like NaCl, and we asked which has a higher boiling point and which has a stronger attractive force, it would always be NaCl, because NaCl has an ionic attraction, a full positive and full negative. So if we're going through order here, it goes like this: London dispersion forces are the weakest. Then you have dip-dips. Then you have hydrogen bonding. And these are all considered to be molecules. Then you have ionic and metallic. And it's hard to tell those apart, like which one is better or which one is stronger. But these are with actual ions put together. Now, just so you're aware, when we talk about boiling and melting points, following the strength of attractions, what we mean is this. If your attractive force, either your IMF or your attractive force, either of those two is stronger, you're going to have a higher boiling point. Why? Because if your attractive force, things holding things together, is stronger, it's going to require more energy to break them apart. And remember, boiling is simply taking liquid molecules and breaking them apart into individual molecules. So if they're held more tightly, like water has hydrogen bonding, so it's held very tightly. So in order to break those apart, we have to raise the temperature of water to about 100 degrees and putting a lot of energy in order for it to break apart. There's other things that literally have very little attraction and they boil at 5 degrees Celsius. Or gas particles that we know in the air, like nitrogen, they have boiling points, and that's crazy to think about hydrogen boiling, of close to minus 200 degrees. All this to say, you need to know what the ranking system is in the order of attractive forces, and the way the molecules put together will help us with that. We'll work together a little more on this in class. Hopefully this has been helpful. You have a blessed day.